Let's start with a simple example. Let's say we have this web application called bidding service, and its job is to increment the bids on a particular item. So whenever there is a request, the bidding service will get the ID from the request. It'll fetch that item from the database using that ID. It'll increment the bid amount by say 1%, and it'll save the item back to the database. So the code to represent this is also very simple. Same three things: get the record, increment the bid, and save the bid back into the database. But if there are multiple requests which want to increment the bid on the same ID or on the same item, so let's say in this case we have the item ID passed in both these cases as 3, and this will cause a concurrency issue because there are multiple steps involved, and we want one request to complete all these 3 operations and only then allow the second request to perform the same operations. If they do it together, it's going to be a concurrency issue, and one way to solve this problem is using locks. First, we'll get the lock for that particular ID. We'll try to acquire the lock. Once we have the lock, then we'll perform those 3 operations, and once the operations are completed, only then we'll do an unlock. So at a time, even if 2 threads try to acquire the same lock, only one will be allowed to proceed, and the other thread will wait until the first thread is able to unlock it. Visually, it looks something like this. So thread 1 and thread 2 both try to do the lock operation. Say thread 1 acquires the lock, so it will go ahead and do the database operations, but during that time thread 2 will go into the wait state, waiting to acquire the lock, and only when thread 1 says okay, I'm done with my operations, I'm doing the unlock operation, then the lock is available for thread 2, and then thread 2 can perform the IO operations on the updated values. And from a CPU perspective, this is also quite efficient, because let's say thread 1 was running on one core and thread 2 was running on another core. When thread 1 acquired the lock and thread 2 was waiting for the lock, instead of thread 2 doing nothing on this core, it is better that this CPU core is utilized, and that is why we push this thread out into a wait state and we allow some other thread to start working on this particular core. To do that, it has to clear off all the registers and L1 cache and so on and so forth, and schedule some other thread. Now let's change this use case a little bit. Now instead of having a database to save and retrieve the items, let's say all that is done within the memory itself. So this time we do not have any database. We are just going to store all the items in a map. The code for it will absolutely remain the same, because even though the item is in a map, we want to ensure that there are no concurrency issues, so we'll still have the concept of locks. But the difference this time is these operations of getting the record, incrementing the bid, saving the record back into the hash map is going to be a very quick operation, because it does not involve the database at all. So in this case, we'll again have thread 1 and thread 2 trying to acquire the lock simultaneously. Only let's say thread 1 gets the lock, it does these quick operations and it performs the unlock, and during that time the thread 2 is in the waiting state. But this time the duration of this wait is, let's say, less than 1 millisecond. So in this case, for only 1 millisecond wait, this would have been the right operations. Both try to acquire the lock, one gets the lock and does the operations, and during that time the thread 2 does not go into the wait. It will again try to acquire the lock multiple times, and eventually after 1 millisecond it is able to acquire the lock, and it continues with its operations. So in this case there is no context switching. The thread 2 never goes out into the wait state and never comes back onto the CPU. In this scenario, since the lock is available very quickly, this is a better option. Yes, so on the CPU, the thread 2 will never go into the waiting state. It will just keep retrying, and during the retries, only for 1 millisecond some of the CPU cycles will be wasted, because there is no actual work that thread 2 is doing. It is only trying to acquire the lock again and again, and that is alright, because we are saving the time of the thread switches. And that is the basic concept of spinlock. Keep trying to acquire the lock. This is not just about the lock class, it can also be about the synchronized keyword. So basically keep trying to acquire the monitor without going into the wait state. This is only efficient when we assume that most of the locks are unavailable only for a very short period of time. And this concept of spin locks are also called as busy loop or a busy wait or spinning. But as we saw, it comes with a trade-off. If the locks are available quickly, then the spinning makes more sense because now you're avoiding the thread switches. But if your lock takes more time, then your thread will keep on trying to acquire the lock again and again and again. So let's say in case of the database operation, we use this concept of spinning. Then in that case, for 300 milliseconds or so, when the IO operation is happening, the thread will keep trying to acquire the lock. No other thread is allowed to work on that CPU core. That concept is called thread starvation. And on the flip side, the typical waiting of a particular thread when it's trying to acquire a lock is good when the lock takes time, because then the thread can go into the wait state and some other thread can be scheduled and it can use the CPU. But on the flip side, if the locks are available very quickly, then there is no point of waiting. Before Java 8, specifically I think in Java 6, we had these JVM flags or options which allowed us to use this concept of spin locks. So we could say use spinning and we could apply a specific threshold. So here we are saying that try 12 times to acquire the lock, but after 12 times you're still not able to acquire it, then go into the wait state. And since it's not very predictable when the lock will be available, these flags are no longer available as part of Java 8. But internally, JVM still uses it, and this concept is called adaptive spinning. Internally, JVM will try to acquire the lock for some threshold amount of duration or for some threshold amount of repetitions, and only when those repetitions or that duration is completed, it will go into the wait state. The JVM will keep profiling your code at runtime and will decide what is that amount of duration or what are the number of repetitions. So that's the simple concept of spin locks. Do not immediately go into the wait state. Try to acquire the lock, and only if after a certain threshold the lock is still not available, then go into the wait state. That's it for this video. Thanks a lot for watching and see you in the next one. Bye.